the giant rocket NASA is building for deep space. For most of human history, the sky was something to look at, to wonder about, and to imagine. Even after the invention of powerful telescopes, space remained mostly a place for observation rather than travel. Only in the last several decades did it become possible for human beings to leave Earth at all, and even now, most crewed spaceflight remains relatively close to our planet. We have sent astronauts into orbit, to space stations, and once, many years ago, all the way to the surface of the moon. But traveling deeper into space is a much greater challenge. That is one reason NASA has spent years developing a new rocket for missions beyond low Earth orbit. This rocket is known as the Space Launch System, or SLS. It is one of the most powerful launch vehicles ever built, designed to carry astronauts, cargo, and exploration systems farther from Earth than any human mission has gone in generations. A rocket like this is not simply a larger version of older launch vehicles. It is a carefully engineered system built to survive some of the harshest conditions any machine will ever experience. At launch, it must endure extreme vibration, overwhelming heat, violent thrust, and enormous structural stress. Every component has to perform exactly as intended. Even the smallest miscalculation in the timing of an engine burn, the pressure inside a tank, or the behavior of a guidance system can affect the mission. The reason NASA continues investing in such rockets is simple. If humans are ever going to build a lasting presence beyond Earth, then they will need reliable ways to send large payloads into deep space. Small rockets can launch satellites. Medium rockets can support many orbital missions. But deep space exploration on a human scale requires something much more powerful. The SLS represents a bridge between the age of earlier lunar exploration and whatever comes next. In some ways, it continues the legacy of the Saturn V, the giant rocket that carried Apollo astronauts toward the moon. But it is also part of a very different future, one in which space travel may become less rare and more sustained. A launch vehicle of this scale is not only about reaching one destination, it is about building a transportation system that can support many future missions. When people imagine space travel, they often think first of astronauts floating in silence above a planet or walking in strange landscapes beneath unfamiliar skies. But before any of that can happen, there must first be a machine powerful enough to lift everything off Earth. And in that sense, a giant rocket is not just a piece of engineering. It is the opening move in a much larger story about how humanity might travel outward into the solar system. How SpaceX changed the way rockets land. For a long time, rockets were treated as disposable machines. They launched once, completed their task, and then fell back to Earth in pieces, burning up in the atmosphere or disappearing into the ocean. This made spaceflight incredibly expensive. It was a little like building an airplane, flying it once, and then throwing it away. That old model shaped the economics of space exploration for decades. Launches were rare, complicated, and costly. Governments could afford them for scientific missions, military programs, or major national projects, but routine access to space remained limited. Then a different idea began to take shape. What if rockets did not have to be destroyed after each launch? What if they could return, land, and fly again? This concept sounds simple in theory, but it is extraordinarily difficult in practice. A descending rocket booster is not gliding gently like an airplane. It is falling from the edge of space at immense speed. To survive the journey back, it must orient itself correctly, control its descent, slow down at exactly the right moments, and then land upright with remarkable precision. It has to do all of this while dealing with changing atmospheric conditions, fuel constraints, and the demands of flight control in a rapidly shifting environment. SpaceX made this idea real. Through years of testing, failure, refinement, and repeated attempts, the company developed reusable boosters capable of returning to Earth and landing vertically. At first, the sight seemed almost unreal. A tall rocket stage descending through the sky, slowing itself with carefully timed engine burns, and settling gently onto a landing pad looked more like a scene from science fiction than something from ordinary engineering. But after enough successful landings, the impossible began to feel familiar. The visual drama never quite disappeared, yet the concept itself became normalized. Reusability changed the rhythm of spaceflight. It suggested that rockets could be operated less like expendable fireworks and more like transportation systems. This has major consequences, not only for launch costs, but also for how often missions can happen. The broader importance of this shift is hard to overstate. If space travel is ever going to expand beyond occasional government missions, then the price of reaching orbit must come down. Reusable boosters do not solve every problem, but they fundamentally change the economics of launch. They make it easier to imagine a future in which satellites are deployed more often, scientific instruments can be launched more affordably, and larger long-term projects in orbit become more realistic. In a way, reusable rockets changed something psychological as well. They made spaceflight feel less like a one-time heroic event and more like the beginning of a repeatable system. And once a system becomes repeatable, it becomes possible to build much bigger ambitions on top of it. The massive Starship rocket and the dream of Mars. If reusable boosters transformed how people think about launches, then Starship has transformed how people think about scale. This spacecraft, developed by SpaceX, is intended to be much more than a simple launch vehicle. It is designed as a fully reusable transportation system capable of carrying large amounts of cargo and eventually large numbers of people beyond Earth. Its size alone makes it remarkable. Starship is enormous, not just by the standards of modern rockets, but by the standards of almost anything ever built for space. The system is intended to lift heavy payloads into orbit, refuel in space, and then travel onward to destinations such as the Moon or Mars. This is an entirely different level of ambition from the smaller, more specialized missions that have defined much of the space age. Mars sits at the center of this vision. For decades, the red planet has occupied a special place in the human imagination. It is cold, dry, dusty, and inhospitable, yet it is also the most Earth-like world in our solar system in some important ways. It has seasons. It has polar ice. It once had flowing water on its surface. And because of that, Mars has long seemed like the most plausible place for a future human outpost beyond Earth. The idea of sending people there, however, is staggering in its complexity. A Mars mission is not just a longer version of a moon mission. It requires more food, more radiation protection, more durable spacecraft, more reliable life support, and much greater tolerance for delay and isolation. Communication with Earth can take many minutes each way. Rescue is effectively impossible. Every system has to work over long periods far from home. Starship is meant to address that scale. It is being developed not only as a spacecraft, but as part of a larger architecture for long-range human travel. The vision includes orbital refueling, repeated use, cargo delivery, and eventually missions that could support surface operations on Mars itself. Whether this exact plan unfolds as imagined is still uncertain, but the ambition is clear. The goal is not simply to visit another world and come home. The goal is to build the capability for sustained interplanetary travel. This is why Starship captures so much public attention. It is not only a machine, it is a symbol of a possible future in which planets are no longer purely remote objects seen through telescopes, but destinations. That future remains far away, and there are many reasons to be cautious about timelines and promises. Yet even so, the existence of such a project changes the conversation. It pushes the idea of human movement through the solar system out of the realm of distant fantasy and into the realm of difficult but serious engineering. Why NASA wants humans back on the moon. After all, astronauts have already been there. The first lunar landings took place more than half a century ago, and those missions remain among humanity's greatest accomplishments. So why go back? The answer is that the purpose has changed. During the Apollo era, the moon was a destination in a geopolitical race, a place to prove what was possible. The missions were short, intense, and historic. Astronauts landed, explored briefly, collected samples, and returned home. What they achieved was extraordinary, but it was never designed to become a lasting human presence. Today, NASA's interest in the moon is more practical and strategic. The moon can serve as a proving ground for the technologies and habits that future deep space missions will require. It is close enough that missions are manageable compared with Mars, but far enough away to force engineers and astronauts to solve problems beyond ordinary Earth orbit. Living and working on the moon involves challenges that closely resemble those of long-distance exploration. There is extreme temperature variation, harsh radiation exposure, abrasive dust, communication delays smaller than those for Mars but still meaningful, and the need for dependable life support. If humans can learn to operate sustainably on the moon, they will gain experience that may later be essential elsewhere. The moon also has scientific value of its own. Its surface preserves a record of early solar system history that Earth has largely lost through erosion, plate tectonics, and weather. Studying the moon can reveal information about planetary formation, ancient impacts, and the environment of the early inner solar system. In addition, some regions near the poles may contain water ice hidden in permanently shadowed craters, a resource that could become very important for future exploration. Returning to the moon is therefore not just about revisiting a famous place. It is about building continuity where there was once only a brief moment of triumph. It is about turning a destination of first footsteps into a place of repeated presence. In that sense, the moon becomes less of a historical monument and more of a next step. What a permanent moon base might look like. A lunar base would almost certainly not look like the gleaming cities often imagined in older science fiction, at least not at first. The first true base on the moon would likely be small, practical, and built around survival. Its design would reflect necessity more than elegance. The moon has no breathable atmosphere, no weather in the usual sense, and almost no natural protection from radiation or micrometeorites. That means a lunar habitat would need shielding. Some concepts involve inflatable or rigid modules delivered from Earth and then covered with lunar soil, known as regolith, to help protect the people inside. Other ideas involve building structures partly underground or using local materials through advanced manufacturing. Inside the habitat, life would be highly controlled. Air, temperature, pressure, humidity, and water recycling would all need constant monitoring. Every liter of water would matter. Every system would be designed with redundancy in mind. Unlike on Earth, there would be no quick replacement for a failed environmental system. Reliability would not be a luxury. It would be the condition for survival. But a moon base would be more than shelter. It would also be a workplace. Astronauts or lunar crews might study geology, test life support systems, conduct astronomy from the radio-quiet far side, and practice extraction of useful resources from local materials. If water ice can be processed at scale, it might eventually provide drinking water, breathable oxygen, and even hydrogen and oxygen for rocket fuel. Over time, if operations expanded, a lunar base could become more than a scientific station. It could become a logistics point, a testing ground, and an industrial foothold. Launching from the moon requires much less energy than launching from Earth because lunar gravity is weaker and there is no thick atmosphere to fight through. In the distant future, that could make the moon an important staging area for missions deeper into space. The image of a permanent base is therefore quiet but profound, not a grand metropolis, but a small cluster of human-made rooms standing in a landscape of dust, shadow, and silence. A tiny place of warmth and breath on an otherwise airless world. And from such small beginnings, entirely new chapters of exploration could emerge. The quiet dangers of deep space radiation. One of the great hidden dangers of space travel is that much of it does not look dangerous at all. In films and illustrations, space often appears serene. Planets glow softly, stars shine steadily, and spacecraft drift through darkness with elegance and calm. But beneath that stillness lies an environment that is deeply hostile to human biology. Radiation is one of the most serious risks. On Earth, our atmosphere and magnetic field shield us from many high-energy particles coming from the sun and from distant cosmic events. We rarely think about this invisible protection because it surrounds us constantly. But once astronauts travel beyond Earth's protective magnetic field, they enter a region where exposure rises significantly. This radiation does not always produce immediate dramatic symptoms. That is part of what makes it so difficult. It is often cumulative, affecting cells over time and increasing the risk of long-term health problems. A mission lasting many months in deep space could expose astronauts to much more radiation than typical missions in low Earth orbit. Solar storms add another layer of concern. The sun occasionally releases bursts of energetic particles that can be hazardous to spacecraft and dangerous to human crews. A major event during a Mars mission, for example, could create a serious emergency if shielding is insufficient. Scientists and engineers are therefore searching for ways to reduce exposure. Better shielding materials are one possibility. Mission design can also help, as can protected storm shelters inside spacecraft, where astronauts could retreat during intense solar activity. Some researchers are even considering whether local materials on the Moon or Mars could be used to shield habitats. The challenge is not insurmountable, but it is central. If humanity wants to move beyond short trips and occasional missions, then it must learn how to live with the invisible physical realities of deep space. Radiation is one of those realities. Quiet, unseen, and persistent, it reminds us that the journey outward is not only about rockets and destinations. It is also about learning how fragile human bodies are and how carefully they must be protected far from Earth. How long a journey to Mars would take? Mars feels close in the night sky compared with the stars, but in practical travel terms, it is still far away. The distance between Earth and Mars changes constantly because both planets orbit the Sun at different speeds and along different paths. When the timing is favorable, the trip is shorter. When the planets are less favorably aligned, the journey becomes longer and far less efficient. With current propulsion systems, a crewed mission to Mars would likely take roughly 6 to 9 months one way. That means astronauts would spend a very long period inside a spacecraft with limited space, limited privacy, and no possibility of turning around quickly if something went wrong. And the travel time is only one part of the mission. Depending on orbital mechanics, crews may also need to remain on or near Mars for an extended period before the return trip becomes practical. This changes the psychology of exploration. A lunar mission is difficult, but the moon is only a few days away. Mars is different. It is distant enough that delay, isolation, and self-reliance become defining conditions of the mission. Crews would need to handle technical problems, interpersonal stress, physical maintenance, and routine life in a confined habitat for many months. Microgravity or reduced gravity adds to the difficulty. Human bodies are adapted to Earth. In space, muscles weaken, bones lose density, fluids shift, and normal patterns of balance and movement change. Astronauts on long missions must exercise regularly to reduce these effects, but exercise itself takes time, space, and equipment. A Mars-bound spacecraft would need to support not just survival, but the physical condition of its crew over many months. Then there is the emotional side of time. A 6-month journey can sound abstract when described in numbers, but in lived experience, it means waking up in the same enclosed environment day after day, surrounded not by weather, cities, and changing landscapes, but by machinery and darkness. The discipline required for such a mission is extraordinary, and yet the fact that such missions are seriously studied tells us something important. Mars is not just a dream in the poetic sense. It is a logistical problem being broken down, measured, simulated, and slowly approached. The journey is long, the difficulties are real, but step by step, the path is becoming more understandable. The problem of carrying enough food, air, and fuel. Spaceflight always comes back to mass. Every item that leaves Earth must be lifted against gravity, and lifting mass requires energy. That means every kilogram matters. Food matters, water matters, air matters. Tools, medicine, clothing, scientific equipment, spare parts, and fuel all matter. A human mission is never only about the destination. It is also about what must be carried to make the trip possible. For missions in low Earth orbit, resupply is at least conceivable. Cargo vehicles can bring additional food and equipment. But for a mission to Mars, the crew would have to be far more self-sufficient. They could not simply request another shipment in a few days. Their spacecraft would need to include carefully planned systems for survival over many months. One important solution is recycling. Modern space habitats already recycle some water and air, but future deep space missions will need these systems to become even more efficient. Waste would need to be minimized. Life support systems would need to work continuously with high reliability. The difference between a viable mission and an impossible one may depend on how successfully a spacecraft can reduce the need to carry endless supplies from Earth. Fuel presents another challenge. Large interplanetary missions require enormous energy. Some mission architectures therefore include refueling in orbit, or even producing fuel from local resources at the destination. On Mars, for example, scientists have explored the possibility of manufacturing methane and oxygen using local materials and imported hydrogen. If that becomes practical, it could change mission design dramatically. This is one reason people talk so much about infrastructure in space. Exploration at scale is not only about building one heroic spacecraft, it is about building systems that support repeated travel, orbital refueling, resource extraction, recycling technology, storage depots, surface power systems. All of these are part of the larger picture. Without them, missions remain rare and fragile. With them, the possibility of sustained exploration begins to grow. Could private companies build hotels or cities in orbit? Not long ago, the idea of private companies building large inhabited structures in orbit would have sounded purely speculative. Yet as launch costs change and reusable systems improve, the idea no longer feels completely detached from reality. It still belongs more to the future than the present, but it is a future that can be discussed in concrete terms. An orbital habitat could serve many purposes. It might operate as a research station, a manufacturing site for processes that work better in microgravity, a training center for deep space crews, or even a hotel for wealthy visitors and specialized travelers. These possibilities are not identical, but they all depend on one thing: access to orbit becoming reliable and relatively frequent. The moment orbit becomes easier to reach, human use of it begins to diversify. Instead of a single government station serving many roles, there could eventually be multiple platforms with different purposes. Some may be scientific, some commercial, some mixed. One habitat might focus on medicine, another on materials science, another on tourism, and another on training missions bound for the moon. As for true cities in orbit, that remains much more distant. A city implies not only habitation, but continuity, services, systems of maintenance, governance, supply, and long-term social life. That is a far greater leap than simply constructing a station or hotel. Still, once people begin imagining permanent orbital communities, they are really asking a deeper question. Can human civilization extend into places that were once accessible only to machines and brief missions? Even a small commercial habitat would mark a major transition. It would mean that space is no longer used only for state-backed prestige missions or isolated scientific operations. It would mean that orbit has begun, however slightly, to resemble a place of ongoing human activity. And once that threshold is crossed, many other possibilities begin to emerge. What space travel might look like 100 years from now. Trying to imagine space travel 100 years into the future is both difficult and strangely calming, because history shows that technology rarely develops exactly as expected. A century ago, modern air travel was still young, computers did not exist in any familiar form, and the moon had never been reached. If someone from that time were shown today's satellites, robotic probes, or reusable rockets, they might find them almost impossible to believe. So the future is uncertain, but uncertainty does not prevent thoughtful imagination. If current trends continue, space travel may become more layered and more ordinary in some ways, even while remaining extraordinary in others. Launches may be more frequent, orbit may contain more stations and more specialized infrastructure. The moon may host small, permanent crews. Mars may have received its first human visitors, perhaps even its first semi-permanent outpost. Travel itself may become more system-based. Instead of one-off missions assembled from scratch, there may be established routes, reusable vehicles, orbital refueling hubs, and mission architectures designed for repetition. That kind of change would matter more than any single launch. It would mean that leaving Earth is no longer treated purely as an exception. There may also be developments we are not yet good at predicting. New propulsion methods could shorten travel times. Artificial gravity systems might reduce the health problems of long missions. Closed-loop life support might become efficient enough for longer habitation far from Earth. Entire categories of orbital industry might appear that are still only theoretical today. And yet, for all the technology, the emotional core of space travel may remain the same. Human beings will still leave one world and look back at it from another place. They will still carry questions with them. They will still move outward with a mixture of curiosity, caution, ambition, and wonder. That may be the deepest continuity of all. Rockets will change. Spacecraft will change. Agencies, companies, and missions will all evolve. But the human impulse to cross a frontier simply because it is there and because something meaningful may lie beyond it will likely remain. And somewhere in that long future, in a quiet spacecraft or a small habitat above a distant world, someone may look out into the dark and feel connected to the first generations who imagined that such journeys might one day be possible.